metrics as we know it is definitely changing. For instance, tag metrics is still something that's been popularized over the past like kind of 2, 3, 4, 5 years. And high dimensionality, I think, is one of the next steps. So once we have, so we used to be in a point, StatsD has dimensions, like you put text separated things one after another with a separator, and each one between those separators is meant to mean a dimension, but it doesn't really have name dimensions. And it was kind of, I don't know, it was very confusing when you're using a lot of the functions in StatsD and working out actually how to like use these dimensions in a powerful way. Then Prometheus came along, popularized all the functions that made grouping by certain tags and rolling up things at query time really expressively popular. And then I think what we're seeing at Uber is now that's being taken to the absolute extreme. And people are putting insane amounts of dimensions on this data, to the point where it's like it's not even clear if it's metrics or logs, because there's so few actual events in some of the tag combinations. But we'll dive into that a bit more in a second. So yeah, I'm going to talk a little bit more about what I mean by high dimensionality metrics, also known as high cardinality metrics. So take a single metric, status code from say an HTTP front end. We have a few hundred important HTTP routes that we want to monitor at Uber, just at the front end. So not even talking about those 4,000 microservices that we have. We might have like a few hundred routes, status codes, less than a few common ones. And we also want to work out this regions and app device version is kind of like specialized to kind of the traffic that we're serving. We serve traffic in New York, San Francisco, Seattle, and the actual responses that are delivered can really it can be affected significantly by some of the configuration on the back end that engineers and product teams do at Uber. So what is failing in Seattle could be a hyper localized failure, and everyone in San Francisco and New York is taking rides just fine. So that's why we like to slice and dice by region. And then by app device version, similarly, some features may break when you roll out a new app device version. So we need to monitor by that. You can roll up these metrics instead of just multiplying all those things together. Like if you multiply 500 by 3, so 500 routes, 3 status codes, 500 regions, 1,000 device versions, that's a massive number. But you can roll these up. So essentially, you're not going to look at a specific city and a specific device version potentially. Like that just might not be as interesting. You may only want to look at like city versus city and app version versus app version, app device version. So so let's say we just want to look at what does the app that we rolled out 4 weeks ago versus the app that we rolled out today look like. So if we want to look, basically work out which route is failing and one versus the other for any of these app versions, we're pretty much going to say take 500 routes, multiply that by 5 common status codes, multiply that by say the 100 app versions that we have out there. That's 250,000 unique time series. It's not bad, but now we start to get engineers they want to slice and dice by more, of course. They want to work out, all right, is that traffic being served by a canary backend service? So some kind of test that you're doing on the back end and back end only versus just the normal production group. Maybe you have some experiments that some of these users are enrolled into, and you actually need to monitor which app versions are affected by different experiments. That's even just doing that, like 250,000 by 2 by 100, that's 50 million unique time series, and that's a lot of metric. That's a lot of time series. Some cases can't be flattened or rolled up, kind of as we're talking about. Even just a few dimensions that have many unique values get out of hand really quickly. Again, 2 examples here. 2 dimensions with 1,000 values is 1 million. 4 with 100 million. Please don't do that. 100 million is a lot. We have 6.6 billion metrics in our index. But if you rolled out a new metric that was 100 million, and we had to index that in minutes so that your alerts could like stay could keep matching the existing regex queries that they have, that it would blow a lot of things up. So why do we even want to use these things if they're so painful and terrible? It is really useful to drill down. Like those cases that I'm talking about, they exist. They're really important. And if anything, people are wanting to like look at everything. I think there's definitely, causes for abuse there, and some people I kind of needlessly instrument things, but there are significant, really good real world use cases where having these kind of dimensions matter, and it helps. So, and why would you do it with metrics? Logs are super high. You can add super high cardinality to logs, and then it's just a function of if you're scanning all these events and then grouping by, storing them as logs is cheaper because you don't have to potentially index them if you do scans. But yeah, it's definitely not very highly compressed, and the scans are slow. Even if you index them, you're storing a lot of raw documents. So metrics actually is quite a good way to solve some of these drill downs. This kind of takes a while to grok, so I'm not sure if it's actually worthwhile, like a good idea to put this on the slide now that I'm thinking about it. But it does have, you can see how like 4 raw events can basically be turned into one event like key, and then you can just kind of show sub-aggregates of when those appear. And that kind of shows that, yeah, when you're doing these queries and you really don't care about some of the subparts of that log data, it is much more efficient to store that as metrics. So I want to talk quickly about why this is important to Uber. We have a lot of microservices. So take that one status code example I'm talking about. We have 4,000 services. Thank God, not all 4,000 microservices actually serve traffic in the same way to the app. They have a smaller domain problem. They're solving a smaller part of the world of that entire request. But they have a lot of tags, and they want to differentiate their metrics as well. So it's used for capacity planning, real-time alerting, basically anything that someone wants to monitor it going south very quickly in say 10 seconds, 30 seconds, or a minute kind of timeline. They use it for that. And we also put a lot of business metrics in there, which is kind of different to how a lot of the normal operational metrics used to traditionally be used. So systems like Prometheus are now starting to also, enable this kind of like almost application business-like metric collection. And I think it's interesting because it does overlap with analytics platforms. So yeah, everything's converging, it seems. Anyway, this slide kind of shows off just a little bit about like the traditional way you'd instrument a small bit of code with metrics and how the dimension, like a response code, gets included. Again, you probably don't want to do it this way. What Austin was talking about, automatically emitting metrics with your middleware, is definitely much more desirable because then you don't have to go and manually spend time every time you write some code. And usually you kind of want to measure it in consistent ways. So if you have 4,000 microservices and what I call latency, you call duration, that's going to be frustrating when you're kind of like digging through different people's metrics. So all this little slight different naming concepts across a whole bunch of the same things causes a lot of pain because it's basically everyone has decorated their house the same differently to you. You can't find where that fork is in that drawer that you have no idea where it must exist. So discoverability is a big issue. I was going to talk a little bit about the fact that, we've built some tools that at least try to, the middleware that we do use puts the drawer in the place where you know where to reach for it. And because of that, it means for any of the 4,000 microservices, we know that if you're using Redis, if you're using Cassandra, your metrics are formed like this. We can discover what tables you're using based on the table tag that your Cassandra middleware is using. Things like that. It means we can build dashboards for you in a way that's very highly contextual. There's a huge value in this. I'd love to see this upstreamed into Grafana. I think actually we've got some teams working on that. So I'd love to actually, hopefully that starts to become a bit easier to do when you're kind of not using like some all-in-one platform that does it for you. And a lot of software as a service companies are really good at actually doing this. They'll give you either one library or one agent, and they'll kind of detect what you're doing and give you nice dashboards and alerts for you. But essentially how this works is, we have you have some business logic and you use some common RPC or storage or caching layer, and that uses the exact same type of metrics and tags it in the same way. And it's kind of all comes together quite nicely when your backend knows what it's doing based on that. Yeah, I think I just wanted to kind of get more at the high cardinality case here. It's pretty obvious that when you start to add a whole bunch of these dimensions, even just to your normal middleware, that's going to again blow up the cardinality. Like you're going to have a lot of metrics because that one team that wanted to see slow queries on a MySQL table, but only if it's a select and group by. Now you have a metric for everyone in the company that has a select and a group by and slow queries. So this kind of stuff is really powerful, but also it costs a lot. Like it's if you were to just store this in OpenTSDB, which is one of the slightly older perhaps metrics warehouses, I guess, that's really expensive and it's going to be really slow to query for. So I think just for some rough numbers, and I definitely, someone will probably get angry that I just pulled them out of nowhere, but we roughly found something like a single OpenTSDB machine, could ingest like 30,000 metrics. And N3DB these days, we've been able to operate it like in a relatively pretty. We're not like pulling our hair out when we run it at 300,000 metrics per second. So that's like an order of 10. And that means that, you can do more of this kind of stuff. It does mean that you can just be a bit more lax. You don't have to slap people's wrists as often if they're over-instrumenting everything. So yeah, exactly. What is so hard about doing all those things? Well, at Uber, now that we're talking about the Uber case study, we have a lot of data. We have something like 400 to 600 million metrics per second, depending on what time of the day it is. And this is, again, just a culmination of all the different metrics from all the different applications running on all the app hosts at Uber. And it kind of generates roughly like 130 gigabits of data. So that, if you've ever copied large files, that it sounds like it might be a large file, but it's and maybe it doesn't even sound that impressive, but you got to remember that a metric is, if you really distill it down to the basic stuff, it's 16 bytes. 8 bytes is a float 64 for the value of the sample you took. And then the other 8 bytes is an int, and that's an int 64, and that's a Unix timestamp or Unix nanoseconds, whichever you fancy. And so basically we're talking about 130 gigabits per second divided by 16 bytes. And that's why that number is actually pretty big and causes us pain. So yeah, after we do the aggregation, that kind of, so basically we're buffering these metrics for about 10 seconds. And we send them at 1 second resolution from all the hosts. So basically, that kind of, you'd think that aggregating for 10 seconds would give you a tenth of the data. Turns out it doesn't, for certain reasons. For instance, like our latency measurements that we take, we actually take a single metric in, and then we explode it out, and we give you a percentile, like a 99th percentile, 95th percentile, a 50th percentile. We also give you a min and a max. So some of these metrics coming in actually get amplified by the different type of aggregations that you're doing on them. So yeah, that's about roughly 20 million metrics is stored individually. So we're definitely not calling them transactions. There's no guarantee. It's definitely not It's definitely not similar to running an insert on a MySQL database. It's because we basically try to make this as optimized as possible. But 20 million unique things coming in and storing them uniquely in different places, it tends to be pretty hard. And it roughly translates to about 50 gigabits per second of data. And we have about 6 billion unique metric IDs. And the reason this is so high, and when I say metric IDs, this is really the time series. Like if we go all the way back to what I'm talking about with this one status code metric, that's just one metric, but it might explode to 100 million time series. So that 6.6 billion number is not the number of metrics, it's the number of time series we store. And the reason this is so high is that it basically accumulates and rolls. People are putting tags in there that are shortly lived. And I can get into that more later. The actual alerts we have about 150,000 real-time alerts. And 2.2 thousand queries per second doesn't sound like a whole lot, to be honest. And basically, 2.2K is 150K divided by 1 minute, roughly. I'm sure the math is very wrong, actually. But we allow certain alerts to be executed more or less frequently. And that's kind of how we're getting to that number. Even though it's only 2,000 queries per second, that ends up being like 30 billion data points. And we read 20 gigabits per second out of and this is 20 gigabits compressed data coming out of the query service. So why M3? So these is all some hard things and why you might want to do them, and why I guess someone's dumb enough like us to do it. Why are we using M3? So as Uber grew, we needed a way to just add capacity to our metrics platform. We were adding lots and lots of machines, and just in terms of like the machines that run everything at Uber. So our data centers were getting pretty full and multiplying pretty quickly. We really didn't want to go down the route of, all right, this team gets a Prometheus server, or this team gets a StatSite cluster. And I think, a lot of people are finding that going from 1 to 2 is hard. Going from 2 to N is even harder. But as soon as you're going from 1 to 2, it really does beg the question, you're probably going to go 2 to N. So when you're talking about how many Prometheus servers you run, your life gets a lot more complicated when you're running 2 versus 1 and N versus 2. Anyway, this was really important to us. If we were going to run metrics for the entire company, we just needed to press a button and add more hardware. The best onboarding is no onboarding. One machine is easier to operate than many machines, but similarly, one cluster is easier to operate than many machines. And the best operator of things are computers. Scripts are great, but after someone does it, runs it the wrong way a few times, you really got to ask yourself, how many more of this can I take? So, we didn't want to rely on teams running scripts to provision more servers and running scripts to point their dashboards to a specific installation of their monitoring cluster or anything like that. So, a brief history, we kind of got there over time. We went from Graphite and Whisper DB, which actually gave us some of those benefits. You can just add a machine, but you have to take the whole system down and reshard it by hand. And that actually is a really big problem. Like, you might think, I just double my cluster every 6 months and we take a bit of downtime. It's not terrible, but also machines die. And also maybe you don't want to, have a very hard coded setup. And perhaps you want to move your entire stack to somewhere else. And sometimes the easiest way to do that is gradual migration of just shrinking and expanding these clusters. In 2015, we started building what we call today M3, and we built it on Cassandra. We had RF2, which means basically we had 2 replicas, and these 2 replicas caused a bit of pain actually as well. So we got our benefit of being able to well, not exactly press a button, but log SSH into a machine, do some things to it, and it would come up, provision itself, join the cluster. So we kind of got elasticity on the clusters we were running, and we didn't have to move customers' configs around or anything when we added machines or removed machines. Turns out that RF2, is actually really painful to deal with operationally. If you lose one node, you're down to one. So you're it's on fire. You're getting paged, and you're worried about that. And not only that, Cassandra has this beautiful property where it replicates writes that. This is configurable. Like you can write quorum into it, and you don't have to worry about hinted handoffs. But at RF2, you can't really write quorum. There's no majority of two. Two is everything. So with RF2, we have to use a consistency setting of 1, which means that it replicates eventually to the second node. Cassandra uses what's called hinted handoffs to basically store this data, and it kind of in a push-based style will push that extra data to the other replica as fast as possible. When a machine goes down for 2 or 3 hours and it's the middle of the night, so maybe, I don't know, maybe someone screwed up the on-call schedule or your baby is crying for 3 hours straight and you don't realize you've got paged. But anyway, I haven't actually had to deal with that with Cassandra, but other on-call issues, I've experienced that. But anyway, so replication with hinted handoffs becomes really painful because Cassandra has a default setting of 3 hours to store those hinted handoffs. So basically, if your node is down for 3 hours and then you bring it back up, it's never going to replicate that data. You basically now have a whole gap. And not only that, if you're actually reading data back in a way that you want to allow that data to be read reliably, you have to, again, do some kind of quorum read. But with RF2, you can only do basically consistency level 1. Because if a machine is down, then you can't even service queries if you're asking for 2 replicas to reply. So RF1 reads when you've missed some hinted handoffs, causes people to log into your IRC or worse version of IRC if you're using a worse version of IRC channel and get angry at you because they're like, my graph is like flipping between these 2 values. Am I going mad? Is your software not working correctly? Is it who is it? And a lot of fingers get pointed in a lot of different directions, and we didn't want to live with that anymore. So anyway, that's a long way to say that we really wanted to run with RF3, repairing that data. So if you get into that case of like your dashboard is flapping because depends what replica you read, the only way for us to fix that is either tell you to please ignore it, and I know it's annoying, or we run a repair on the cluster, which basically works out where does the 2 replicas not agree, and maybe we'll stitch the data back up. Repairs on our clusters, when our clusters got big, took something like 15 hours. And we had a retention period of 2 days in our really high resolution metrics cluster. So you're basically missing that data anyway for 15 hours. And not only that, that's 15 hours on 1 node. And we had like 50 nodes. So to actually run a repair to stitch up, fix that issue they saw, it's basically impossible. And by the time you've even repaired even a small fraction of the cluster, you've already, the metrics already dropped out of retention. And the reason Cassandra does that so bad is essentially Merkle tree. It uses Merkle trees to actually build an idea of how the replicas don't agree. And building Merkle trees are expensive and slow, and definitely doing it in a general way is painful. And Cassandra has a very, very expressive general way of modeling your data. Anyway, yes, expensive SSDs was also a really big kind of stickler for us. Early on, we just kind of asked the company to just keep giving us expensive stuff, and they agreed because they didn't want to be in the middle of a really high traffic day and have to put up with not having metrics. But then when the company got a little bit bigger, they definitely got less happy. So with 1,500 hosts, and we're talking about pretty expensive hosts, that definitely was something that the company got upset with. So M3 was really about being able to operationally do this easy, but it started to become about cost as well. And kind of what's funny about this talk and like why I really wanted to express how important a role high cardinality metrics are having today is that cost actually is really important when you're talking about high cardinality metrics. If you want a whole lot of power and you don't want to spend more than a few percent of your entire compute spend on your application, you should care about this stuff, because otherwise you're not going to be able to get that high cardinality data. You're going to basically kind of give up or monitor less. But again, you don't want to abuse it, but it's starting to it's starting to slip into a lot of middleware. So I think it's unavoidable at this point that people are going to keep doing this, and this trend of high cardinality metrics is only going to continue. So yeah, in 2016 we started writing some things that backend that wasn't in Cassandra for M3, and it was a pretty painful journey, and we were having to put up with Cassandra the whole time, but it worked out for us. What are the design principles for it? So again, it's kind of optimized for high read and write. The cost is a real big stickler for us. We want to give engineers we want to empower engineers to really instrument as much as they can, get as much out of their middleware as possible, and not break the bank. So and the other thing was, for us, like, we didn't want to be called all the time and worry about hinted handoffs, how long a node was going to be down for. I mean, ideally, you have some automation to recover from a node being down. You don't actually have to wait for a human to press a button. But there's a whole bunch of these like small operational death by 1,000 cuts that Cassandra, especially when we're talking about metrics data, was kind of painful for us to use. So we wanted to make it a lot easier to run for people at large scale, essentially, but also at the small scale, and being able to just gradually add more nodes in a way that wasn't super painful. So yeah, I mean, I can talk a little bit more about when I talk about how we're different to other people. Thanos and Cortex are other kind of like open source scalable metrics platforms, much like we're an open source scalable metric platform. But they definitely optimize for different things. We really, especially based on how our usage of Cassandra, we wanted to reduce compactions. Compactions is, a thing in a lot of these storage systems that basically make it faster to read and allow you to take a super high write volume because your data is actually not sitting right next to each other. Similar in like B-tree, kind of based storage systems. But it's we found compactions like are really painful, especially when you're talking about data that's just going to roll out. If you're talking about data it's kind of like it's your user data and it's going to be there for a really long time, it makes a whole lot of sense for over time you just spend a bit of like your compute power making that a super like as optimized as possible. With metrics, you're literally collecting stuff and then you're throwing it away. So compactions for us just didn't really make sense, and it also made our the hardware profile a lot more expensive. There's another reason why we do a lot of our downsampling up front before actually the data goes into our storage layer. So even Thanos, they have something called a compactor role, and you run compactions of these compressed blocks, and you stitch together all this data, and then it goes up somewhere else, and it's in a format where you can actually read it fast. But again, it's now actually this other method that you have to think about. All right, compaction lag. Like, how long did it take? How far behind is my compaction for downsampling metrics? And so basically, you can imagine the scenario of you keep data for 10 seconds at 2 days, and then 1 minute and 30 days, the same data. And you want to view it based on how far you back in the past you're looking at. You want to use the 10-second data or the 1 minute data. The if compaction lags by 2 days, now you have no data to look at that's not in 1 minute format yet. Because your 10-second data that you kept is rolling off, and your 1 minute data hasn't been generated from the 10-second data that you wrote in. So you play a game of chicken essentially whenever your compaction starts to lag, and kind of not only that, it's also it's just an operational burden to have to basically be monitoring how this large kind of batch process is occurring in the background. And another thing that we've actually noticed, so we're actually just talking today to some people that use Atlas, which is Netflix's monitoring open source database. I mean, it's purely in memory actually, so it's kind of more for like short-term metrics, or you just throw a lot of hardware at it and use metrics. The memory for storage. But the way that they go from, say, a 10-second 2-day cluster to a 1 minute 30-day cluster is, so 1 minute, and when I say like 10 seconds, I mean that's the period that's the timestamps you're collecting at 10-second granularity, and you're storing that for 2 days. Similarly, with if you're collecting data for 1 minute at 30-day period, it's obviously not as finer grained. But it's cheaper to store for longer amounts of time. Basically, we were talking to these people that were using Netflix Atlas to store their data. They kind of need to do this interesting thing, and we actually needed to do this when we had a similar strategy with Cassandra, where you basically take some of the if you actually look past 2 days, and you say you do a 7-day query, you have to select all the data that hasn't been put into 1 minute tiles yet, from the 10-second resolution 2-day cluster. I wish we had a whiteboard to actually draw this, but sadly we don't. Yeah, you basically end up with this gap where you haven't produced the 1 minute tiles yet for some of this data, and you now basically have to downsample live from the 10-second day cluster and merge that with 1 minute tiles from the 30-day cluster. I mean, you can avoid doing it, but what's going to happen is, because stuff is at 10, say you take a counter of your counting requests per second. If you don't downsample that 10-second data when you stitch it together with the 1 minute data, then you basically have if you were just requesting collecting constant value of 2 every 10 seconds, then when you look at the 10-second data, it'll be 2, 2, 2, 2, 2. When you look at the 1 minute data, it'll be 12, 12, 12, 12, 12, because there's 6 10-second tiles in a 1 minute tile. So you can't really put 2, 2, 2, 2, 2, and then 12, 12, 12, 12, 12 right next to each other on a graph, even if the timestamps are respective of like where you actually collected that data. It just looks weird to someone. They don't understand, and it doesn't make sense to actually put different sampling, show data that's sampled at different rates on the same graph. So traditionally what you do is you take that 10-second data, you combine them all up to 1 minute granularity, and then you can actually look at the graph and it looks steady. The issue with all that is now you basically have to do this live downsampling process at the query time. And it also is slower because you're basically fetching a lot more data points from the more finer granular cluster. So, because we do this at ingestion time now, it's we can just go straight to the 1 minute tiles. We have that 1 minute tile. We computed it for you just as it arrived. Yes, you might have a lag of like up to 1 minute because that's how big the tile is, and we're not going to finish the tile until you were at least a minute behind. But it ends up being like the queries become a lot faster, and it has just been a lot easier to deal with. So that's another big win we've found with M3. I was going to talk a little bit about how we store all this stuff and how the database node works. I mean, honestly, it's pretty basic at a conceptual level. It's really just every metric is a key in a key value database, except that for the value of that key, we kind of have an array of these compressed metric chunks, and each chunk is relevant for a different point in time. So you might have for metric foo, some buffer that represents the time between 12 to 2 p.m. for metric foo, and it's basically a byte buffer that's just highly compressed using TSZ compression, which is a float64 optimized compression algorithm. And then you'll have 2 to 4 p.m. and then 4 p.m. to 6 p.m. and so on and so forth. So that's what the format for a key in the key value store looks like. And then we also do similarly to a lot of other LSM databases, we write the actual raw data points coming into a commit log, which we call a write ahead log, which we call a commit log. That's just because this key value format of the actual persisted files are basically all together, and we can't write that out until we've collected all the data for an entire time window. So we need to save that data basically as it comes in before we finish the time window, because otherwise the time window is literally just resides only in memory. And so when we boot up, we can read all the key value data files, and then we basically read all the raw values for the values that haven't been flushed yet to a key value file set. Anyway, I did want to spend some time. We're trying pretty strongly to get some people using this, and I did want to kind of spend some time on how best to use it and where should people get started. So this is what the open source story today for M3 looks like. If you are basically already running Prometheus servers and you kind of want to basically scale up or scale down and see all that data together, you can, if you have a way to map Prometheus server to N machines that you're monitoring, you can start to just export all the data from those Prometheus servers to M3, and you'll get a central store. You won't have to mess around with data sources in Grafana, and you won't have to kind of do a lot of discovery when you're trying to find your metrics. So yes, you can use what we have today in open source is you basically have this sidecar called the M3 coordinator that sits on the Prometheus server. You write to that over the Prometheus. You set in your Prometheus config, hey, I want data that comes into Prometheus in real time to be sent to this sidecar. Then that sidecar will essentially write all the real-time data into M3DB. And M3DB is clustered and has basically its own index, the time series storage engine, and etc.d, which is you can think of etc.d very similar to Zookeeper. It's a config store. It's strongly consistent. It lets us add stuff like the membership of the cluster and keep track of those things. Nice thing about etc.d is it's written in Go. So we kind of do this semi-Frankenstein thing where we basically pull in the etc.d as a library and then run a embedded etc.d cluster alongside our M3DB cluster. This just makes it a little bit easier so you don't have to run yet another type of server role when you're kind of working with M3. And then, optionally, if you like, you can push data in yourself. It doesn't have to be just coming from Prometheus. We have a Go client. We also have some endpoints on M3DB itself under basically both the M3 coordinator and M3DB have the same read and write APIs. So you can push data in directly. And then, the future. So yes, you may have some Prometheus instances and you may write your data to M3, but and you can do it potentially yourself. We really do want to be able to let people run Grafana and basically point their Grafana instances directly against M3. This way, you kind of don't have to deal with the whole, I guess, option of like letting Prometheus run your queries. So it kind of gives you, I guess, a more direct source to your data, as well as kind of allowing, if you actually set up like Grafana alerts and stuff like that, so you do your alerting out of Grafana, it may be simpler to just point it to M3DB rather than individual Prometheus service. Or you can, again, write your own alert engine. So anyway, yeah, we also really want to support stats D metrics in open source. We do use M3 for stats D metrics and tag-based metrics and Prometheus metrics. It's just that, yeah, we basically don't have some of that plumbing in the open source repository just yet. We're actually pivoting a lot of our internal deployments of M3 to use purely the open source components, so that, you know, over time, the way that we run M3 is the way that anyone else would run M3. So as part of this shift, Graphite and StatsD support will start to come to M3 soon. And then what does your roadmap look like real quick? We want to, yeah, again, add support for Graphite metrics. We want our new query engine to be a little bit more, we need it to be more feature complete, and we want people using it, make it more useful by, you know, of course, supporting Graphite as alongside PromQL, which may be difficult, but hopefully not too much. And then we want to make it easier for, so once basically it's super easy to use for any kind of use case and deploy it anywhere, which is a big part of it. Where, you know, we're working on a Kubernetes operator. We want community, like there's been a community submission even recently for a Terraform module so that you can run M3 on AWS. That's the kind of thing where we want to make it super easy for a whole bunch of different use cases first. And then, we basically want to kind of get to this picture where the aggregator becomes a lot more easier to use as well for larger scale types of deployments where you care a lot about losing data on the way in. With Prometheus, you basically have to run an HA setup, and it's not always super easy to configure it and do so in a lossless way. But basically, we want to build three major components that can all be swapped in for anything else. So, you know, depending on no matter how you kind of run your monitoring and your organization, you can kind of pick and choose which parts of it you use from M3 or from other people. I don't know if that kind of cleanly describes it, but moving right along, yeah, I think the best practices I really wanted to kind of get at here is it comes all the way back to, why do we even build M3? Adding and removing capacity for your metrics platform should be easy. So that is really the here we are today, and how I think things will change very significantly when it comes to a lot of our instrumentation. It's like when we only had MySQL. You know, you only had MySQL, and MySQL is honestly great for a whole lot of things. And in fact, you know, we're using projects at Uber all the time with MySQL. It has a single write master, and you have to set up slave replication. It's not easy to cluster and kind of scale out. And so, you know, you have to kind of like really pick and choose and think really hard about when you're going to use MySQL, when you're going to use something that's clustered out of the box, that kind of thing. The same thing with metrics. You know, it really should be like, hopefully the clustered thing is free and available, and you don't have to go for the single non-clustered thing from day one. Hopefully you just deploy a single instance and that works as well. As a clustered version, it's the same technology. You don't have to swap everything out when you go from 1 to 2 or 2 to n. So I think really, yeah, definitely, you know, when we get a little bit more community support, you shouldn't have to think hard about running these things, because it's a burden. You know, we've done it. We've tried to do a better job at it, and would love some other people's help on and doing it better as well. And it shouldn't be a nightmare to run this stuff. This stuff is next generation. In some ways, like I really think high continuity metrics is just going to continue to be a huge theme that we see. Yeah, right now we have some documentation, a mailing list, Gitto, which again is like RSC, but it's not, unfortunately. And you know, I think we'd love to add some screencasts, some more guides, some integrations that are like one click to get started in a certain environment, or that kind of thing. Yeah, thank you.